Hi, everyone. Thanks for coming out today. My name is David, and today we're talking about distributed task scheduling at PagerDuty. So first, a little bit about me. I'm a software engineer on the core team at PagerDuty, and it's composed of these fine people on the right here. The team is mostly in Toronto, but the company has offices in San Francisco and Seattle as well. And on the core team, we support many different engineering teams at PagerDuty. So this is mostly by building shared libraries and infrastructure and researching best practices. One thing I want to emphasize is all the ideas I'm talking about today, we worked on together. They're not my own ideas. I'm just the guy lucky or maybe unlucky enough to be standing right up here. In particular, Alexei, who's on the left there, did much of the design work for this project, so kudos to him. So do we have any PagerDuty customers in the room? Let's see some hands. OK, awesome. So you know what we are, but for those of you who are not familiar, we are a software as a service company, and we do IT incident management. So what that means is that we aggregate data from monitoring systems like New Relic or Splunk or Datadog, and we create incidents when something bad happens based on rules that you set up. So an incident might be something like the database server crashed. So when an incident is created, we alert people who need to know about it through push notifications or phone calls or SMS. And these notifications usually go to someone who's on call. So there's actually on-call scheduling built into the system. So long story short, our customers rely on us to let them know when something is wrong with their systems. And this is a really big responsibility, and one that we take very seriously. So because we take this responsibility so seriously, we think a lot about reliability and uptime. And the most important piece of this is the notification pipeline. So if something is wrong in your system, you need to know about it, and there's no excuses. So to achieve high availability in the face of catastrophic failure, our infrastructure runs in 3 different data centers. And everything that we build is expected to survive the failure of one of those data centers. So keep this requirement in mind as we go through the talk. When I talk about a data center failing, this is a very real thing, and our business requirements dictate that we handle it well. So why are we here? Today, I'll introduce our problem, which is a distributed task scheduler for use at PagerDuty. I'll talk briefly about what the old solution was. Then I'll describe our new solution. And this is the one built with Akka, Kafka, and Cassandra. After that, we'll spend a good portion of our time talking about how the team used those 3 technologies to solve some interesting distributed systems problems. Finally, we'll talk about the results of our project. OK, so the problem. In terms of the product, here are some use cases that we're trying to solve. So our system supports many types of notifications. If you're going on call, you might want some warning about that, and maybe you want it 2 days ahead of time, so you remember, don't party too hard. And then when you're actually doing your on-call shift, you need to be notified that an incident happened. So we have very customizable rules for this. Maybe you want a phone call immediately, but you want a push notification 1 minute later to make sure that you're actually awake and out of bed. Another use case we have is retrying notification delivery. So we have redundant SMS providers, but what if they're all down for some reason? We need to schedule a retry in that case. So those are specific examples. But actually what we have is a very generic problem. We have these arbitrary chunks of Scala code, which we'll call tasks, and they need to run at an arbitrary time. And this code might do anything. It might be synchronous, it might be asynchronous, it might talk to a database, it might start your car. It's included in many different microservices at the company. And when I say arbitrary time, that means it could be scheduled for 1 second from now, or it could be scheduled 1 year from now. At the same time, it has to be tolerant of very dynamic infrastructure. So like I said, we currently run in 3 data centers, but it could be 4 next year, or we might have to add or subtract 10 machines from one of our services. And some of those machines or data centers might be down when a task is scheduled to run. Or all of the machines in microservice might be entirely different VMs from when a task was scheduled. But despite all this, we need our tasks to run in order. So ordering is a complex thing. Let's define it a bit more exactly for the purposes of this system. So we're going to say that task 1 is only guaranteed to execute before task 2 if these 3 things are true. Number 1, they have the same ordering ID. That is, a developer said these things are linked and I want their ordering to be defined. Number 2, task 1's scheduled time is before the scheduled time of task 2. That makes sense. And lastly, the call to schedule task 1 was completed before the call to schedule task 2. And that last bit is important and a bit tricky. So let's have an example here. Let's say that we have 2 tasks and they're scheduled very close together, and they're scheduled for a second from now. So task 2 might execute first if the scheduling call completes before it does for task 1. But we have some room to make things easier as well. So tasks only need to be executed within seconds of their scheduled time. We're not talking about millisecond precision. We can also delay task execution arbitrarily to preserve our ordering. Also, the tasks are idempotent, and this is a very important point. If you run them a second time, nothing bad is going to happen. Lastly, our tasks rarely fail, but they do sometimes, so we have to be prepared for that occasional instance. Okay, maybe this is just a simple matter of programming. You can just knock it out in an afternoon. Well, let's find out. So PagerDuty has an existing solution to this problem, and it's been around for a few years. It works, but there's some room for improvement. The old solution was called work queue. This is a very simple version of how it worked. So the components are shown in green on this slide. Now, some of my coworkers in the audience are probably, shaking their heads right now because I have this all wrong, and but sorry, I just joined the company in January, so I don't really know how it works. Anyway, we have this Scala service. It's scheduling a task through an API, and the work queue writes that task to a wide row in Cassandra. Now, a wide row means that the queue is a row in Cassandra, and the task time is actually the column. We have another component that's pulling Cassandra for new tasks and executing them using a thread pool. This is pretty simple, and it works. But what about when you have many service instances trying to pull from the same queue? In other words, how do you distribute the tasks to the available instances without duplicating work? So to solve the problem of having multiple service instances, we introduced custom partitioning logic into work queue. And the partitioning logic puts tasks into different wide row queues in Cassandra, and each service instance works a partition, which is basically hard-coded. It's not, but we won't get into it. And then there's some logic to handle a service instance going down. So each partition actually has a primary, a secondary, and a tertiary partition or instance that would work the queue. And these instances would be peeking at the queues to make sure that the progress was being made, and they would also do health checks on each other. And if a service instance fails, the system would handle it, but it's kind of a big deal. Like, people would be paged in the middle of the night because the system is now in a degraded state. So what's changed from our previous diagram? We introduced some pretty complex custom partitioning logic. And now our work queue library needs to be aware of how many service instances there are and how many queue partitions there are, and what happens when you need to add another one. Things get kind of hairy. So the old solution works, but it has some problems that we wanted to address. So like I was talking about, adding or removing a service instance was quite a complicated dance due to this custom partitioning logic. There's actually like 7 different steps. You need to like converge chef and like restart a service and do some deployments, and I don't even know. It's not something you want to do at 3 a.m. when Amazon decides to kick one of your boxes. The old solution was also quite slow, so the only way a task was executed was by pulling it from Cassandra. So we're actually hammering our Cassandra clusters with these very slow reads. And this frequent slow I/O actually influenced decisions on where to place our data centers physically. So they're all currently on the west coast of the US, so that latency between our Cassandra nodes is minimized. This is in large part due to work queue. We also have a huge reliance on this complex partitioning code that was really maybe only understood by the handful of people who wrote it or have to deal with it often. That's not a good position to be in. Okay, enter the new Hotness. It's the same as the old Hotness, but it's on fire. Earlier in this year, the core team built a new solution to the same problem. And very originally, we named it Scheduler. It's not actually on fire. It's working quite well, and we're going to find out how. So the new scheduler library is built in Scala, same as the old work queue. And it uses 3 different technologies to tackle various challenges. Now, I'm assuming most of you have some idea of what these things are. But in short, Kafka is a distributed commit log. And if you saw David McNeil's talk yesterday about Amazon Kinesis, a lot of that is going to apply to Kafka as well, even if the terminology is slightly different. Cassandra is a distributed NoSQL column-oriented database based on ideas from Google's famous big table paper or also Amazon's Dynamo. And Akka is an actor system library for Scala or Java. So if you're not familiar with actors, they are computational entities that run in parallel and communicate by sending each other messages. Okay, definitions out of the way. So this is a very high-level diagram of the new scheduler and how it integrates into our services. So again, we have some service that's written in Scala. It's shown in red here. It includes scheduler as a library, shown in green. It's actually 2 separate libraries, one for the client and one for the implementation. The service's logic schedules a task by passing it into a schedule task method. And the library, in turn, serializes the task and enqueues it to Kafka. Now, it's important to note here we're just serializing task metadata. We're not actually serializing any sort of task logic. On the other end of the queue, you have scheduler itself, which consumes tasks as they are sent. Now, it's always going to persist the task to Cassandra, but if the task is scheduled before a certain time in the future, it's also going to remain in memory. At the same time, scheduler is also fetching tasks out of Cassandra on a regular basis, similar to the old work queue. And then this combination of in-memory tasks from Kafka and fetch tasks from Cassandra is executed by calling a task executor defined by the encompassing service. So you, as the library user, need to define how the tasks are executed, and that's how we get away with not serializing any task logic. Now, this looks somewhat similar to the old version, but a major change here is having Kafka in the mix as well as Cassandra. So the purpose of this talk is not to explain exactly how every part of scheduler works. Instead, I would like to talk about some of the challenges typically faced when building this type of system, and how we use those 3 technologies to help us solve those challenges. Everybody knows distributed systems are hard. They have many challenges. I'm going to focus on some 3 main areas during this talk. So dynamic load, which is really a problem for anyone, data center outages, and task ordering. We'll start with dynamic load. So what happens on Black Friday when everything is happening all at once and everyone's systems are going down, and at PagerDuty we're sending out a much higher number of notifications than normal? Specifically, what happens when you start scheduling more and more tasks? So there's a number of components that will need to keep up with the increased load. But let's start with Kafka, since it's first in the pipeline. So generally speaking, Kafka will scale horizontally. That is, we can keep adding brokers to our cluster to deal with the increased number of tasks. And this works because for a queue, which is called a topic in Kafka lingo, there are n possibly replicated partitions. So these topic partitions are spread evenly across the available brokers, such that each broker gets an even share of the traffic, and therefore an even share of the disk I/O, and etc. And what's quite nice is that if you add or subtract a broker from the cluster, Kafka can rebalance the partitions to ensure the load is still even. So let's take a look at how this works. We'll start with 2 brokers, and we have 1 topic, and that topic is divided into 6 partitions. Each partition is replicated once from a leader to a follower. All the reads and writes are going to the partition leader. So in the case of a write, the leader forwards the write on to its followers. And this leader-follower stuff is important. We're going to see it again in the presentation. So in this example, each broker is a leader for 3 partitions and a follower for 3. Okay, let's say we start exhausting disk I/O on our 2 brokers. So we add a 3rd to the cluster. The partitions are redistributed by Kafka. This is something you have to manually initiate, but the process itself is fully automatic. So now each broker is a leader for 2 partitions and a follower for 2. Each broker only needs to deal with 4 partitions instead of 6. Okay, again, we're going to scale out now to 6 brokers. Each broker is now only a leader for 1 partition and a follower for 1. And as you can see, for this to continue scaling, we should have significantly more partitions in our topic than expected brokers. This example is not going to scale further than 12 brokers. At that point, you have each broker is either a leader or a follower for a single partition. Adding more brokers to that cluster is not going to help. But there is also a cost to having a very large number of partitions per topic. It can affect availability and end-to-end latency, so this is not something you want to increase beyond reason, and you can do some Googling to learn more about that. So that takes care of scaling Kafka. What about the service itself? Well, again, we can scale horizontally, and this is actually enabled by Kafka. So the consumers of a given topic, which in this case are service instances, are grouped together, and this is called a consumer group. The group's healthy consumers are tracked by Kafka through a heartbeat mechanism. The topic's partitions are distributed evenly to the healthy consumers, and this is a dynamic process. So if consumers die or consumers are added, the partitions are reassigned. So here's an example with a topic that has 5 partitions. With 2 service instances in the same consumer group, one service gets 3 partitions and the other gets 2. Okay, now let's say our 2 service instances can't keep up with the workload, so we add a third. Kafka is going to automatically reassign those partitions such that they are evenly distributed across the 3 instances. Each instance is now responsible for 2 partitions at maximum instead of the previous 3. This is called a consumer rebalance. And Kafka can do this very quickly, but typically you're actually limited by how fast your application can react to that consumer rebalance. So in our particular case, for scheduler, it's actually about 30 seconds. Again, note here that the scaling is not effective once your number of instances equals your number of partitions. Your instances, for them to be useful, have to be working at least 1 partition. So this is another thing to keep in mind when choosing the number of partitions for a topic. So our service instances are receiving the tasks from Kafka, but now they have to persist them somewhere. So we're using Cassandra for our task persistence, and like Kafka, it will scale horizontally. Now I'm kind of assuming that many of you know about how Cassandra scales, so I'm going to go through this pretty quickly. It's not terribly interesting. The key for a Cassandra row is going to be hashed into a token in a known very large range. And the nodes in the cluster are each assigned a range of those tokens. So therefore, a given row will go onto a known node in the cluster. Then as you add nodes, the original nodes become responsible for a smaller range of tokens. So in this example, we have 4 Cassandra nodes. And to make the math easy, we're going to say that the range of tokens is 0 to 99. In reality, this range is going to be much, much larger. So that range is evenly divided into 4, with each node being responsible for the previous 25 tokens. So for example, node 1 is responsible for 76 to 0. Node 2 is responsible for 1 to 25. So when we insert a new row into the cluster, Cassandra is going to hash that row key to get a token, and the token dictates which node the row will go on. In this example, the token was calculated to be 80, so it lives on node 1. Now, this doesn't take into account replication. A row is usually replicated, which means it's going to live on multiple nodes in the cluster. It also doesn't take into account Cassandra V nodes, which is a more complicated feature, which I won't get into right now. Okay, so our 4 nodes are having trouble keeping up. We'll add a 5th node to the cluster. We actually have to shift the tokens around so that they are still evenly distributed. Each node is now responsible for 20 tokens instead of 25. And this is an oversimplification that you probably wouldn't do in production, but I think it helps understand the concept. I also learned that it was very difficult to draw this in Google Drawings, so I didn't want to make it any more complicated. Okay, so our setup can handle changing load. We can add machines to our various clusters to scale horizontally. But what happens when an entire data center goes away? You know, what happens when someone at Amazon trips over the internet cable? Well, we'll start with Kafka again. Our setup is to have 6 brokers evenly split across 3 different data centers. So you have 2 brokers in each data center. Now, each partition has 3 replicas, 1 per data center. Again, we want to be very sure that we're not going to lose any data. In Kafka 0.10, you can actually ensure 1 replica per data center through configuration, but we are still running Kafka 0.9, so we actually do this through some custom scripts. So when we do a write, we ensure that it's replicated to at least 2 data centers before the write returns success. Now, normally, if all 3 replicas are in sync, the write will actually go to 3 data centers. But if 1 replica falls out of sync, we will write to 2 brokers and still succeed. And that's what those configuration settings mean on the slide. So if a data center fails, a third of our partitions will lose their leader. But Kafka will automatically change the leader to one of the in-sync followers. And all the reads and the writes are going to go to that new leader. So here's an illustration of how this works. This is a very similar example to our actual setup. The only change is the number of partitions, which makes the diagram a little clearer. So we have 3 data centers, 2 brokers in each one, and there's a single topic which has 6 partitions. So originally, each broker is a leader for a single partition and a follower for 2 others. Okay, and we just lost data center 3. So Kafka is going to shift our partition leadership. Partitions 3 and 6 had a leader in data center 3, which is now gone. So Kafka is going to make broker 1 and broker 4 take on leadership of partitions 3 and 6. And the partitions circled in red have changed from being followers to being leaders. The other thing to note here is that now we only have 2 in-sync replicas for each partition. 2 is the minimum number of replicas in our configuration, so writes are still going to succeed. Okay, so Kafka makes it look easy. Let's look at Cassandra. What happens with Cassandra when we have an entire data center go down? So we have configured Cassandra to deal with this scenario. Simply speaking, we have 5 nodes spread evenly across 3 data centers. And our replication factor is actually 5, which means that all Cassandra nodes are eventually going to get a replica of each row. We want to be very sure that we don't lose any data. And we do quorum writes, which means that at least 3 nodes must acknowledge the write before it returns success to the application. And 3 machines means that we will be in at least 2 data centers. Then we do quorum reads to guarantee that we will get the latest value. Now, maybe some of you are thinking that this sounds kind of slow, synchronously writing to nodes in 3 different data centers. And it is somewhat slow, but we can get away with this because these Cassandra writes are generally not user-facing. So this diagram illustrates our quorum write. In the worst-case scenario, where 2 of your writes are to nodes in the same data center, you are still guaranteed to get a write to a node in a second data center. And again, when you hit the worst-case scenario, we just lost data center 1, along with the 2 nodes that have the new updated value. We're still going to be OK. So we're going to do a quorum read. That means that 3 nodes must respond. And we still have 3 nodes, which will respond in the remaining data centers. But nodes 4 and 5 have old values. So do we still get the new value? And the answer is yes, and we're relying on Cassandra's policy of last write wins here. The value on node 3 has a newer timestamp than the values on nodes 4 and 5, so it will actually be returned. And yes, your clocks need to be well synced for this to happen. We do have plenty of alerting around that. And if you really start diving into the corner cases, it can get hairy. So you should generally try to avoid actually mutating your data. So that takes care of our data persistence. Now let's talk about what happens to the service itself when a third of the nodes go down. Well, as we have seen before, Kafka will detect that those consumers are no longer healthy. It will reassign the topic partitions to the remaining healthy instances. And this works for 3 reasons. Number 1, any service instance can work any task. Number 2, the tasks are idempotent. So if a task is halfway done when the DC disappears, it can be redone by another machine without anything bad happening. And of course, we don't run our servers at max capacity. We're over-provisioned such that we can lose a third of our machines and still deal with the load. So let's say we have 3 data centers and a service instance in each one. The topic partitions are evenly spread out across the service instances. And notice that in data center 3, the service instance is working partition 3. Well, and we lost data center 3. So Kafka will detect the failure of service instance 3 through that heartbeat mechanism, and it's going to reassign partition 3 to service instance 1. The system is going to continue to work. Okay, finally, we need to talk about task ordering. This is a pretty tricky problem in distributed systems, but if you limit the scope of your ordering, it can get a lot easier. And maybe you won't need to use vector clocks, which would be great. So how did we limit the scope of our ordering problem? We have this concept of logical queues for which ordering is defined. Each task has an attribute called ordering ID, which defines the logical queue that it's in. So, for example, an ordering ID might be user ID 123, which means it's in the user ID 123 queue. Now remember that a Kafka topic is composed of many partitions, and we need to put the task into a single partition. So the partition ID is just a hash of the ordering ID modded with the number of partitions. And this takes care of the scheduling side. So here's an example. We have 4 tasks that have ordering IDs based on the user ID associated with the task. Task 1 might be an on-call notification, and task 3 might be an off-call notification. And they're both going to the same user. And let's say they're scheduled very close together. You're only on call for like a minute, and it's the best week ever. So you want the on-call notification to go out before the off-call, because otherwise the user might be confused. So ordering has to be defined for those 2 tasks. So the hash of the ordering ID leads the 2 tasks to be put into the same Kafka partition. This means that they will be executed on the same service instance. Or in a more complicated case, task 1 will be executed, then there's a consumer rebalance, and then task 2 is executed elsewhere. The important part, though, tasks 1 and task 2 task 1 and task 3 will not be executed on different machines at the same time. So on the execution side, we have one service instance executing a logical queue. But of course, the number of logical queues is very high. If we tie the ordering to the users, we could have millions of logical queues. And obviously, we don't want to have millions of service instances. So one service instance is actually executing many logical queues. But to maintain ordering in a logical queue, if a task fails, you need to keep trying it until it succeeds. And you can't be executing any tasks after it. So how can we continue to execute all of the logical queues except for the one that has a stuck task? So the answer in our case was an actor system implemented in Akka. You could certainly do it other ways, but we found that Akka made the needed concurrency to be simple. Each service instance has this Akka system, which is somewhat simplified. And on this diagram, the ovals represent actors, and the arrows represent supervision. So at the top is the topic supervisor. It receives all of the incoming Kafka messages for a given service instance. Now, since a service instance will be consuming multiple partitions, there are partition supervisors for each one, and they are children of the topic supervisor. Within each partition, there are multiple logical queues based on the task's ordering ID. The partition executor supervises an ordering executor for each ordering ID. Now that's potentially a lot, right? Because we have like millions of users, and that could be a lot of different logical queues. But actors are cheap. In Akka, they have something like 300 bytes per actor in overhead, so we can actually get away with having many of these things. The ordering executor has a queue of tasks to execute. It will take the task from the head of the queue and create a task executor for it. Now, a task executor is actually a short-lived actor. It's not going to create a task executor for the next task in the queue until the first one finishes. The task executor is going to retry the task until it succeeds, or in some cases, if it's dropped by a human, if it's never going to succeed. So if a task continually fails, the logical queue contained within the ordering executor stops. But the other ordering executors will continue working through their own queues. So the ordering in the system is maintained, but only where it matters. Okay, maybe you're thinking enough theory. Does this thing actually work? Well, it does. Scheduler has been in production since March. It powers everything that happens in PagerDuty's on-call handoff notification service. So if you use PagerDuty and you've received emails or SMSs saying that you're going on-call or off-call, Scheduler is actually the piece of software that made that happen. And it does a fair bit of work. So millions of tasks are executed each month. And in addition to that, it handles some very interesting spikes. So people tend to change their on-call schedule on the hour. So we do large amounts of work on the hour or the half hour. We're also continuing to do development work on this service, which means multiple rolling deployments per day. Scheduler ensures that those deploys don't disrupt the tasks that are being worked on. And maybe some of you are wondering how we know all this data center outage stuff actually works. Well, our answer to that is Failure Friday. And this is something we do every Friday. We purposefully break our infrastructure in a very controlled and planned way to ensure that the system can handle the failures. So back in May, we actually simulated a data center outage. We killed all the machines in one data center and made sure the system kept on working. It did. Then on July 19, one of our data centers in Azure actually experienced some very severe network problems, which largely cut communication to our other two data centers. This is a worst-case scenario where you have two pools of machines that are still working, but they're not really talking to each other. Well, again, the service performed as expected. But did the new scheduler actually solve the problems from the old work queue? Now, if you remember earlier in the presentation, I said that difficult manual steps were required for infrastructure changes. Lots of chef work, very easy to get wrong. Well, now we can actually add or remove service instances by just killing or spinning up a new box. Kafka's consumer rebalancing ensures that each box will get an equal amount of work and no partition will be left behind. So I can actually type a couple commands into Slack, and our infrastructure automation will bring up a new box. It will join the correct consumer group, and it will get to work. I also said that the old work queue had low throughput because it was frequently accessing Cassandra. With the new scheduler, Cassandra access is down 65%. And this is because the new scheduler pulls for tasks at a much longer interval. So it can do this because Kafka is always feeding it new tasks. This is actually a graph of number of Cassandra reads in production on our guinea pig service. We switched over to the new scheduler at the red arrow, and you can see that the number of Cassandra reads drops quite dramatically. Lastly, I said that the old work queue had complex partitioning logic that only a few people in the company understood. Well, in the new scheduler, the partitioning logic lives in Kafka. It's off the shelf. There are great docs, which are easy to understand, and there's many people outside of our company working on it, and they understand it quite well. This is a much better situation to be in. So in short, yes, it did solve our problems. One last thing, Scheduler is an open source project. So here's the GitHub repo. I will say that using it is a bit more complicated than just dropping it into SBT. You need to have Kafka running and Cassandra. And the docs, they need some work yet, but we're working on it. But the code is out there, and you should give it a look. If this sort of stuff sounds interesting to you, and you're looking for a new challenge, come talk to me or any one of the other PagerDuty people here at the conference. We're always hiring, and we love to chat. And now is the time for questions. It's actually very hard to see you out there. Any questions? Yeah, go ahead. Oh. Yep. Go ahead. Hey.
So with your cross-data replication or cross-data center replication, can you talk a little bit about the Zookeeper topology specifically? Did you encounter any challenges with that, as that's kind of a dependency for Kafka?
Sure. So to repeat the question, you're asking about for cross-data center replication, what does our Zookeeper topology look like? Is that accurate? Okay, so Zookeeper is used by Kafka. Is that what you're talking about in this case? Okay. So I'm not aware of anything special that we're doing, actually. Kafka is using Zookeeper and it's doing its thing, and yeah. Other questions? I don't see any, but yell it out if you have one. In the back?
If your events are apparently side affecting, say, sending a text message, how do you enforce the item potency of those actions in the face of failure?
Yeah, that's a good question. So the question is, if some of the tasks are side affecting, they send out a notification or something like that, how do you enforce the item potency of the task? So the answer is that in some cases, and this is application dependent, but in some cases, the task is actually stored somewhere. So the task has some kind of state that's stored in Cassandra, and if you run it a second time, it's actually going to see that the task is already completed. It's not going to run it again. Does that answer your question?
I think so.
Okay. Anyone else? No? Okay. Thanks very much.